In this video, we'll be taking a look at the Worldbreaking of Hyrule, specifically the version from the 2017 game Breath of the Wild. We'll examine what makes sense according to real-world physics and geology, and what doesn't. We'll zoom out and start from the highest level, which is the Planetary system. At first glance, the world of Hyrule looks very similar to Earth. There's a sun, a moon which has different phases with an 8-day orbital cycle. There are also stars and meteorites in the form of star fragments. But if you just take a closer look at the constellation, things start to break down. First, the stars aren't moving. Normally, this is hard to notice, but if you speed up the footage, it becomes very obvious. And there's just no explanation for this if we want to use the astrophysical framework in our work to analyze Hyrule. Second, while the moon does move, the lunar cycle also doesn't make any sense. The moon always rises at sunset and goes below the horizon at sunrise. This has two implications. First, the sun and the moon are always on the opposite side of the planet, which we'll call Hyrule for simplicity. This means that the moon is at the L2 Lagrange point of the Sun-Hyrule system, so that the three objects are always in a straight line. The second issue is that this would imply that every day is a full moon, but that is obviously not the case. I think the easiest explanation for this is that the moon is not being lit by the sun, but instead self-luminous. If this is the case, it can also explain the origin of the star fragments, which also glow. Since there aren't any other objects in this solar system, the moon is literally the only source that can supply the fragments. A self-luminous moon can also explain the blood moon phenomenon. In the real world, a blood moon happens during a lunar eclipse, which must happen at the full moon. While in Hyrule, a blood moon is also the full moon, it does not follow the lunar cycle. A blood moon can take place the day after a new moon or just after another full moon, which is not possible on Earth. But if the moon is glowing on its own, it can be any phase or any color it wants to be. Another cool implication of the lineup of these objects is that theoretically, the tidal cycle on Hyrule should be very large because the gravitational bulge of the sun and the moon are in the same places. It should add up. But if we actually go to, for example, the Lorelin village, we see that the sea level does not change in the slightest. And on the topic of gravity, we can also calculate many interesting properties of Hyrule using gravity. Calculating gravity is much easier in the sequel game Tears of the Kingdom, which uses almost the same physics engine for our purpose, but shows the coordinate in the corner. It means that by either counting the frames or just straight up running the game in the simulator, people have figured out that the gravitational acceleration of Hyrule is 28 meters per real-world second, which is almost 3 times the value of the gravity on Earth. It has also been found out that the maximum falling speed Link can reach without a paraglider is about 60 meters per second. There is a maximum speed because air drag increases with speed until it balances with gravity, so an object no longer accelerates. Because air drag is proportional to the air density, these information can be used in tandem to determine the air density of Hyrule. If we use the classic and totally valid approximation that Link is a cylinder, we can rearrange the force balance equation to find that the air on the surface of Hyrule has a density of 1/40th that of Link. So if Link is a normal person, the air density in Hyrule is 25 kilograms per cubic meter, which is 20 times heavier than on Earth. The physics doesn't physics in another way, because when Link goes higher up in the atmosphere, there's less air around Link to slow him down, so the terminal velocity should go up. But even if you clip out of bounds to go 50 kilometers up in the air, the gravitational acceleration is still 28 meters per second square, and the terminal velocity is still 60 meters per second. This means that the air density is constant from the surface up to 50 kilometers, which must not be the case because the consequence of an isopycnal atmosphere is that it is very easy to create convection, and it should be raining every afternoon, which would drive everyone crazy. And finally, let's look at the geology of Hyrule. The first order questions we are interested in are, is plate tectonics or something similar operating on the planet of Hyrule? And if so, what tectonic settings is Hyrule in? And there are two main lines of evidence that we can follow. The first is the ore deposits found throughout the world, and the second is the landscape itself. Starting with the first one, the minerals found in both this game and the real world and that are tectonically relevant are diamonds, rubies, sapphires, topaz, and halite. Diamond is a high-pressure mineral, which means it forms deep within the planet, and it must also be brought to the surface relatively quickly before it becomes graphite. On Earth, large crystals of diamonds are usually found in a type of rock called kimberlite, which forms from magma that originates in the mantle. They're usually found in very old Precambrian continental crusts. Technically, you can also find microdiamonds in the highest grade of metamorphic rocks, but they're usually too small and probably don't have the space to develop the crystal habit as seen in the in-game pegmatites. Ruby and sapphires are actually just different varieties of the same mineral called corundum. This is usually found in pegmatites near the edge of deep magma intrusions, where after most of the magma has crystallized, the remaining material becomes highly volatile and rare earth material rich, allowing the growth of large and rarer crystals. The formation environment is also similar for topaz, but I must note that the sprite of topaz in the game does not look anything like topaz at all, but rather more like pyrite, which develops the cubic shape. The last mineral I care about here is rock salt, or halite. This is the only one of the 4 listed here that actually forms on the surface, usually from a restricted basin such as a lake drying out. In fact, it is a prominent theory that the halite is left behind by the ocean in the game The Wind Waker. So to sum up what we have learned from the mineralogy, we need a very deep magma chamber to bring diamonds up to the surface and a stable environment to preserve them. We also need a shallower, more differentiated magma to produce the corundum and topaz, as well as a way to bring them to the surface. From the rock salt, we know that there was a widespread water body in the past, and for it, we need an erosion event to break down and remobilize the rock. In simpler words, we need a lot of magma and a lot of elevation changes. We now turn to see whether the geomorphology is consistent with the mineralogy. The most prominent features on the map include a sea to the south and east corner of the map, a highland and continuous valley in the north and west beyond the world border, 2 north-south striking mountain ranges separated by the Hyrule Field, and the Death Mountain on the eastern range. Death Mountain, a text-spoke stratovolcano, is a very clear sign that there is active volcanism happening here, and another piece of evidence is the Geoling peaks, which are cut by the Squarbo River. This landscape feature indicates that the river must have existed when the terrain was still flat, and has continued to incise downward as the mountains are being uplifted, even though you can quickly realize the river network of Hyrule is a hot mess, and for some reason, none of the rivers drain into the ocean. A real-world analog of the Geoling peaks could be the Taroko Gorge in Taiwan, one of the most geologically active places on Earth. Both platforms supports the idea that at least the east side of the map is tectonically active, and since both features are found on Earth, tectonics seems to be a very appealing mechanism for explaining Hyrule's topography. To answer what exact plate tectonic configurations Hyrule could be set in is more challenging because we must keep in mind that the world map is unrealistically small. It's only about 8 kilometers by 8 kilometers, which is much smaller than even Tucson. Therefore, we must assume that the map is a compressed representation of the actual size of the world to some degree. Nonetheless, I would still like to assume that there are only 2 plates involved in Hyrule, because I don't like the idea that there are a million microplates confined in such a small area. If we keep this in mind, we can see that everything within the world's border looks very much like the North American Cordillera, just flipped east-west. Using this framework, we can hypothesize that there is a plate with an oceanic crust that is subducting westward beneath the continental lithosphere. This would be in a coastal magmatic arc, perhaps associated with an accretionary prism complex. There is a back-arc basin between the 2 mountain ranges, and there's even an inland mountain range that could correspond to the Foreland Thrust Belt and the Foreland Basin beyond it. In fact, during the Cretaceous, much of the North America was submerged under the shallow western interior seaway, whose retreat in the Paleogene could be an analog for the water body that eventually deposited rock salt across Hyrule. The only features unaccounted for by this model are the North and West Highland Valley pair and the host rock of Diamond. I think the valley is the most puzzling landform here. Its profile resembles a U-shaped valley that one could find in glacial landforms, but there is no other morphological evidence of glaciers ever occupying Hyrule. Another candidate is the Rift Valley. However, the plate triple junction geometry doesn't really work out, as the valley lies on the overriding plate, yet somehow still terminates at a plate boundary. I thought about it really hard, and the explanation I hated the least is that the valley is a reactivated normal fault. Such structures can be found on Earth where the mental dynamic topography that used to support the high elevation is gone, and the mountain undergo gravitational collapse. This explanation allows us to identify the plateau as a craton, and the east-tipping normal fault geometry is consistent with the thrust belt structure. The slip on this fault has to be abnormally high, but this is the best theory I can come up with. I will not discuss the biology of Hyrule in detail, as most species are either clearly magical or have a clear biological basis. So to conclude what else we have learned about Hyrule. First, the moon is at the outer launch point and is likely self-luminous. Second, the atmosphere in Hyrule is much denser than Earth and may be unstratified. Finally, the Kingdom of Hyrule is set in a Cordilleran type subduction zone with potentially a collapsing craton interior.